Namaste, namaste to everybody and welcome back. In the last lecture we looked at the idea of dot product between two vectors, and we figured out that if the dot product of the two vectors is 0, then the vectors are orthogonal to each other or perpendicular to each other, that is the angle between them is 90 degrees. And we said that the dot product is also what's called as the inner product, it's also called as the scalar product, and we said that the dot it's basically the sum of products of the components of the vectors that we take. So for towards the end of the last lecture we said that okay, we were able to figure out that if the dot product is 0, we said that the angle between the vectors is 90 degrees. So how are we going to find out the angle between the two vectors when the angle is not 90 degrees? If it is going to be something else, how are we going to find that? So that is a journey that we are going to embark on, but before we get into that we will just look at a couple of properties of dot products which will actually come handy for us to look at the angle between them. So let us look at some properties of dot product. Dot product. So let us look at the first thing. Let us assume that here is a vector that I have which is basically the vector u. I am going to have u1 u2. Now I want to look at what is u dot u itself. What does that mean? I want to look at what is the dot product of a vector with itself u1 u2 dot u1 u2. So we know that the dot product of the two vectors is basically the component wise product and then summing the component wise product. So I am going to get u1 square plus u2 square, which is precisely what we call as the square norm of the vector u. That is a squared length of the vector u, right. And we remember when we did this we said that if u square is such that if it is 0, if u square is 0, this implies u1 square plus u2 square is 0. And we also said that in the previous lecture that if u1 square plus u2 square is 0, you know that u1 square is a positive number and u2 square is a positive number, and you have sum of two positive numbers which gives me 0, which cannot otherwise happen if u1 u2 are real numbers. And therefore we said that if u1 u2 square, if the vector squared norm is going to be, or the norm of the vector is going to be 0, then we say that the vector u is basically the 0 vector. Only if the vector u is a 0 vector, then you get the norm to be 0. So we get u dot u is nothing but u1 square plus u2 square, which is u square. So this is the this is one of the interesting properties of the dot product. The second one that we are going to look at is so let us look at this first property. So the second one that we are going to look at is, let us assume that I have two vectors, namely u, and I have this vector v, where u is this vector u1 u2, this two component vector, and v is the vector two component vector v1 v2, and let w be this vector which is a resultant of this u vector and the vector v, u plus v. So what is it that we have? U plus v is nothing but u1 plus v1 and u2 plus v2, and that is basically my w vector. Now let us look at what is the norm of this w vector. Norm square of w vector is basically, suppose if you assume that this is equal to, let us say, w1 w2, the two components of the w vectors are basically w1 and w2, which are essentially equal to u1 plus v1 and u2 plus v2. So w square is going to be w1 square plus w2 square, which I am going to write this as u1 plus v1 the whole square plus u2 plus v2 the whole square. So essentially what am I going to do? I am going to write this as, let us say, I am going to write this as, let us say, u1 square plus 2 u1 v1 plus v1 square plus u2 square plus 2 u2 v2 plus v2 square. Now this I can write this as u1 square plus u2 square plus v1 square plus v2 square plus 2 times u1 v1 plus u2 v2. Now this is something interesting. You have u1 square plus v2 square, which we already know, that is nothing but the squared norm of the vector u. v1 square plus v2 square, something we already know, which is nothing but the square norm of the vector v square, plus 2 times what we have is u dot v, that is basically what we saw, 2 u dot v, u1 v1 plus u2 v2. Yeah. So this is interesting because I am going to do something here. So the w vector is basically taken as the u vector plus v vector. Now I wanted to find out the squared norm or the squared length of this w square, which is nothing but, let me do it this way, this is nothing but the vector w dot itself, w dot w, which is nothing but u plus v dot product with u plus v, and we can write this as, we already saw this expression in just a minute back, we just saw this expression which was equal to this one squared norm of this plus this one, excuse me, plus 2 times u dot v. This is what we had, right. Now let us, so what we have is, if you look at this expression and if you look at this expression, we see something interesting. This is nothing but this expression that we have here, it boils down to u dot u plus v dot v plus you have u dot v plus v dot u. That is what this boils down to. So what we have essentially, if you are taking the dot product of the sum of two vectors with itself, u plus v dot product with u plus v. So what we get is, we get u square, sorry, this is plus here, I am sorry, that is plus u plus v dot u plus v. So you have u square plus v square plus 2 times u dot v, right. And this is, we just sorted out that u dot v or u plus v the whole square is basically this, and in our pursuit to figure out the angle between two vectors we established this, but we will use the same result to figure out what is the angle between two vectors. So let us look at that now. So what we have is, let us say I have this vector which is u, and I have this vector which is, let us say, v. Okay, let me have this as vector v. Now what we have is the following, we have this perpendicular which is basically here, and this is going to be the angle theta. Now we know that this is going to be u cos theta, the cos theta component of the vector, this is going to be u cos theta, and this is going to be the height, which is nothing but the magnitude, the height is going to be u sin theta, the magnitude of the vector multiplied with the sin theta, or the vector h is equal to u sin theta, right. So now what we have is, let us look at this. So we have h squared is equal to absolute, or the vector length, the squared length of the vector u square sin square theta, right. This is what we have, which is also the same as the length squared into 1 minus cos square theta, right. Now we also see one more thing here, and what is that? Let us look at this. So we are going to look at this. Let me try to draw this u as minus u here. So this is going to be the minus u vector, and this height is again going to be the same h. So this is going to be the height vector h. So what I am going to have is I am going to have this, the v minus u the whole square, the squared length. So this is going to be v, the entire thing is v minus u the whole squared. So we are going to have the height is equal to, let us write this. So I am going to have the height h is equal to we have v minus u the whole square v minus u the whole square minus of modulus of v, I mean the length of v minus the length of u cos theta the whole square. So what is this? This entire vector is v. So what we have is this is going to be, and this is going to be u cos theta, this is going to be u cos theta. So what I am going to have is v minus u cos theta is going to be that. So we have v minus u cos theta whole square, and this is going to be v minus u the whole square. So we are going to have the vector height, the height is equal to this. So what do we have? We have v minus u the whole square is equal to, we already know we can expand this as a minus b the whole square. So we have v squared plus u squared, that means the squared length, minus 2 the length of u the length of v cos theta. Now we also have from our knowledge of squared length we also understand. So what we have is we also understand that, so we also know that v minus u the whole squared is equal to, we have the dot product of v minus u with itself, v minus u dot v minus u, which is nothing but what we have is v squared plus the squared length of u minus 2 u dot v. Now let us take this as equation 2, and what we had in the previous case, let us take this as equation, let us say 1. So what we have comparing 1 and 2, what we get is the following, comparing one and 2 we get 2 u dot v is equal to 2 u dot v is equal to 2 u v cos theta, and therefore what we have is u dot v is equal to u v cos theta, and from there what we have is the cosine of the angle between the two vectors u and v is cos theta is equal to u dot v divided by the length of u and the length of v, the length of u and the product of the lengths of the two vectors u and v. So now what we have is, so this is basically what we have, and we can call this, like where we have this 2 u v cos theta, this is basically my law of cosines. That we would have studied in our class 9-10 trigonometry. So if theta is equal to 90 degrees, we see that u dot v is 0, u dot v is equal to 0, which implies I mean u and v are orthogonal to each other. I mean that is already seen. When theta is 90 degrees, we see that u dot v is 0. That means whenever you have the dot product is 0, then we say that if u dot v is 0, then this implies u is orthogonal to v, right. U is orthogonal to v, that is it. So, what we want to do is we want to figure out like what is the what is going to be the so we already know that cos theta is going to be a value between plus or minus 1. So, what we do is we want to figure out what is the nature of this u dot v dependent on the angle. So, we are going to make a few comments here. So, comments. If theta is equal to 90 degrees, cos theta is equal to 0, which implies u dot v is equal to 0. So, if theta is, I am quite sure all of you know about acute angle and obtuse angle and stuff. If theta is acute angle, then we know that cos theta is greater than 0, which implies u dot v is greater than 0. If theta is obtuse, then cos theta is less than 0, which implies u dot v is less than 0, right. So, this is something which we have to understand, right. So, this is between this is the kind of angles, this is how we calculate the angle between the two vectors. Now, what you do is if you want to figure out if two vectors are linearly independent, now what you do is you figure out if u dot v is not equal to 0, if u dot v is not equal to 0, naturally the vectors are going to be in two different directions, and you can say that they are linearly independent. Even if it is if it is equal to 0, then they are again in linearly independent. I mean they are linearly independent because they are in two different directions, they are orthogonal to each other. If theta is 0, so let us look at that. If theta is 0, then what happens? We get u dot v is equal to u v cos 0, which is nothing but the product of the norms, right. If this happens, then the vectors are in the same direction. Okay. So, now what are we heading to? Where are we heading to? So, having identified the angle between the two vectors and stuff, we are getting into the idea of orthogonal projections. We get into the idea of orthogonal projections. Now, what is it to say projection? Why is it that we are looking at orthogonal projection? Are there any other projections that we have? First of all, we look at the idea of orthogonal projection. So, a projection of a vector, what does it do in another direction? Projection of a vector u in the direction of v what does it do? It basically gives the it's basically telling you what is the kind of okay, let me write this. So, this basically creates a footprint, basically creates a footprint of say some length given by just projection of u onto v. So, we are going to get the projection which is nothing but u cos theta. That is the footprint length that we are going to get along the direction of v. Okay. So, let us look at what it is. So, the orthogonal projection of this is something which we already know. For example, you assume that this is the vector v and this is the vector u. Now, if I project this, that means I just take it is like I kind of hit this guy u at the head and then that falls into the direction of v. So, what is the length that I am going to get? I am going to get this length which is u cos theta along the direction of v. Is that okay? That is what we are going to look at. So, how are we going to look at this projection? So, we are going to look at orthogonal projections. Of course, these are all very elementary ideas that we are doing right now, but we will when we look at projections from the vector spaces perspective, we will deal all these things in more detail, but this is just to give a flavor of what it is to orthogonally project a vector in the direction of the other. Okay. So, orthogonal projection of u onto the direction of v. We will say u onto v, which is basically written as projection of u onto the direction of v. So, that is basically given by, we already know what it is. This is nothing but u cos theta and along the direction of the unit vector in the direction of v. So, this is going to be into v divided by this. Remember that this guy was actually giving us the unit vector. This guy was basically giving us the unit vector along the direction of v. So, you have u into cos theta. So, what is cos theta? We already know that cos theta is, so let me write this, u into u dot v divided by so let us write that. So, I am going to have u, and how did we define cos theta? We had it here, u dot v divided by u into v. So, let us use the same thing, u into u dot v let us go back here. So, you have u dot v divided by u dot v divided by u length of u into length of v in the direction of the unit vector, which is v divided by this. So, you can see that these two can be knocked off. So, I have projection of u in the direction of v to be equal to u dot v divided by the squared norm in the direction of v. Is that okay? In fact, we will see at a later point of time that the projection of u onto v is basically the best approximation of u that you can get along the direction of v. Is that okay? So, that is what your orthogonal projection is, and we already said that this is going to be u cos theta. Projection of u along the direction of v is given by u cos theta in the direction of v, and therefore we also have the perpendicular component, which is nothing but u sin theta. So, let us look at that, the perpendicular component. So, we are going to say, okay, this is basically u cos theta and this is going to be u sin theta. Yeah. So, how are we going to look at the, so we already know that the vector u is basically you can decompose into two components, which is like say u cos theta plus u sin theta, that means u parallel and u perpendicular. So, that is very clear from here. So, this is the vector that we have here, this can be decomposed, this u can be written as u cos theta plus u sin theta. So, that is what we are going to do here. So, let us look at that. So, the vector u that we have, which we just projected onto the direction of v, we have the vector u which can be decomposed. Can be decomposed into two orthogonal components. Into two orthogonal components, namely let us say we will call that as u parallel and u perpendicular. So, I am going to write u is equal to u parallel plus u perpendicular, where u parallel is basically the cos theta component or the cos theta component and u perpendicular is basically my the sin theta component that I have. That is going to be my sin theta component, right. So, we have basically you can actually the what would you say, you can resolve a vector into two of these components. So, what we will do is you will say u perpendicular is basically the vector u minus the projection of vector u in the direction of v, that is u minus u parallel, right. That is the notion that we are going to have for our orthogonal component, right. That means what have we done? We have basically removed the horizontal component to get the perpendicular component, which is basically what we get as u perpendicular, which is orthogonal to the component which is u cos theta. Is that okay? So, that is what we have, and so to summarize what we have done in the entire module, we studied the idea of the summary of the module, overall module. We studied the idea of vectors and points, ideas of vectors and points. We looked at we defined or we looked at points as fixed reference with respect to a particular coordinate system. Vectors can move here, there, everywhere, and we said that points are fixed coordinates, fixed with respect to a coordinate system. We said vectors can move everywhere, vectors are not fixed, and we studied some operations on the vectors and points. So, we call them as coordinate dependent and independent operations. We studied that. We said that if you want to add 2 points, it basically depended on the coordinate that you the coordinate axis or the reference point where you place the origin and stuff, whereas vectors it was not the case. Then we looked at the idea of barycentric coordinates, and we also looked at convex combinations of your vectors. We looked at the length of the vectors or the norm of the vectors through the Pythagoras theorem. So, we looked at length of vectors, then we looked at combining vectors. Basically, we looked at linear combination, and then we looked at the idea of combination of vectors. We looked at the idea of linearly independent and linearly dependent vectors, and how the angle between the two vectors comes into play, saying okay, that makes sense. So, in the sense like if they are along the same direction, they are parallel vectors, then there will be dependent vectors. Any angle other than 0 is going to give me linearly independent vectors. We said that, and we said that if you have linearly independent vectors, the linear combinations can help you cover the entire space, like you can go to any destination that you want, whereas a linearly dependent set of vectors you will not be able to do that. Then we looked at the idea of dot product to find out if a pair of vectors is orthogonal or not, and then we ended up looking at the length of the vector through the dot product, and we said that if the dot product is 0, then that is possible only with the 0 vector. Then we looked at the idea of finding the angle between the two vectors, which we looked at in terms of the cos theta. We looked at finding out the angle between the two vectors. We found out it can be expressed as u dot v divided by u into v, the length of u into length of v, and then we covered the idea of projections and so on. In the next lecture, what we will do is we will try to look at what is it to say mapping a vector. I mean, what do you mean by linear maps of vectors? We will just get, again we are going to deal with only vectors of 2 components each. So, we are going to look at that, and we are going to look at some interesting ideas there, like how do we transform vectors, what are the kind of operations that we do on vectors, and how are we going to capture in terms of matrices, and that will be the set of lectures that we have lined up for the next module. Thank you.